Hi. Hi everyone. I hope you're able to hear me. If not, just put some message on YouTube live and we'll have it addressed. And hope everyone is doing well and ready for today's session on neural networks for classification problems. Today, here we have Sai Gayatri Vadali. She's a data scientist at Tetrasoft and a seasoned data science and machine learning instructor. And the interesting part is her area of expertise and interest lies in deep learning. She has been working on several projects on this front, especially at her workplace. And in this session, we'll be covering various fundamental aspects related to neural networks for classification problems, which includes MLP for classification, loss functions, optimizers, and activation functions. And it will also be a hands-on session using a digit recognition data set. Uh, with that, I'll let Gayatri take over the session. Gayatri, please.
Hi everyone. Hi Chanukya. Thanks for making me a part of this. Um, so today's session we are going to talk about neural networks, a little bit of activation functions, about optimization functions that we use, and multi-class classification. Um, so this is based upon taking into consideration of what has been taken up in the previous session. We will try to build on top of it. Okay. So, first thing, so before we get started, a little bit about the motivation of what a artificial neural network is. You must be knowing it very clearly by now, but uh, for for making a right beginning. So we all know this artificial neural networks. They are inspired by our human brain itself and the cells called perceptrons, which are in our human brain, neurons, which are in our human brain, and based upon these, like taking them as the motivation, these neuron idea has come up. So so the idea was to model the human brain, the way any information passes through neurons. So that was the idea by which they have come up with some mathematical function like sigmoid to create this. So that is the motivation behind creating this neural networks. So so when we look at the way a neural network, like, because as I told, the motivation comes from the human neuron cell. So if we look at it, it's like from different dendrites, information is moving to cell body, and that's how it comes out through axon. So this just a replication I just wanted to bring out. So these are nothing but the input layer, which is which is nothing but the input values which we are giving. I'll explain how we will be giving the input values, and they are being sent into this activation unit. This is called as an activation unit, where usually we apply sigmoid. Or so when we are in the as we go through the session, we will learn about activation functions, right? So this is where we apply the activation functions. And once we get apply an activation function, which is nothing but a mathematical function, we get some output. So that's the idea of creation of this neural network. So it is quite interesting if we look at this perspective, right? So now let's move forward a little bit. And just remember that these inputs are being multiplied with the weights corresponding to the each weight. We have certain each input value, we have a corresponding weight that is being multiplied, and we are getting into this activation unit. Everything will be clear as we keep moving forward. So that is the structure of a neural network. So you must have been looking at this for quite a long time. So this is nothing but the activation unit, and these are here in this particular artificial neuron. There are about three inputs, so x0, x1, x2, and corresponding. Okay, this is the bias. X1 and x2 are the two inputs, and we have added a bias unit. So these are like we multiply x1 times w1 plus x2 times w2 plus 1, because one time w naught 1 times w naught. So that is being sent into this unit. So till here it is nothing but a simple regression, like we are just trying to multiply the weights with the corresponding inputs. So after we come here, we apply some kind of an activation here. So if you look at it here, This is nothing but the bias. X naught is nothing but a constant which is associated with bias, and x1 and x2 are the input values which we are giving. So once we give these values into this, that starts the one, then we will get a mathematical expression for which an activation is applied. So let's look at those activations clearly. So once this activation is applied in this particular unit, we get corresponding output. So if it is a single neuron neural network, this is nothing but the input, and this particular arrow will directly correspond to output. But because our neural networks have like more number of layers as well, which we will look a little bit forward. So there could be a possibility that from a single activation unit, we are not directly getting the final output. There could be intermediate outputs also. Okay, I'll explain what that is. So when
Gayatri,
you, yeah,
before we jump in, I think GIFs may not appear on PDF. So if you want to switch
okay,
to PPT, you can. Yeah, I'm sorry. Yeah.
okay, okay, yeah, sure. Give me a minute.
Yeah.
Yeah, yeah. So this makes more clear. So we have multiplied W1 times X1, W times X2, and W naught times 1, and we have added it. So then we are applying this activate. This is where the activation function comes. And finally, we're getting the output. Thanks a lot, Chanukya.
Yeah, no problem. Thanks.
Yeah. So, so this is what happens in a single neuron. So let us see what happens when we have a set of neurons and they form a network. Uh, let's go a little forward. So here, the same thing which has been explained here, that's what I'm trying to show in another example. So till here, we are just multiplying the corresponding weights and the input units, and we are adding them. This is the summation part. And finally, we are applying a activation function. That's what we have seen even in here. First, we added them. First, we applied a dot product, added them, and then we applied an activation. Okay. So this thing we have just seen for a single, this particular neuron here is what we have seen here. So like that, there are not just one neurons in between. We have added four here, and we have added about two layers. So that's how. So here we are applying activation. Here we are applying activation. Here also we are applying activation. It's if we think mathematically, it is like function of functions, right? So that's how from input it is being processed here, it is being processed here, it is being processed here, and finally we are getting an output. So one more interesting observation which I want to state here is that if we take this, because today we are dealing with neural networks for classification, this particular neuron can give us two values. It can give us two values, that is, it can either tell us yes or no or 0 or 1. So like that, so this particular neuron, so after processing lot of data, we are able to get about two outputs. It could be any of that. So that shows that this is a binary classification. This particular neuron, we can use it for a binary classification as well. A little more I'll tell you as we go forward.
Yeah. Gayatri, can you enlarge the screen so that, that's a request from the
Okay.
YouTube live chat.
Yeah,
Yeah.
okay, is it fine now?
Yeah, it's fine. Or you can present it directly. Maybe even that should be fine, I guess. Anything works. Yeah.
Okay. Present it directly in a sense.
So there is this present button, right? On the,
Okay.
yeah.
Okay.
On the right bottom, maybe. Right bottom. Yeah. Just,
Mhm.
yeah, just below that. Uh, yeah, just, yeah, next to it.
Okay,
Yes. Yeah.
slideshow.
Yeah.
Okay.
Slideshow. Yeah. Yeah.
Okay.
Perfect. Yeah. Thanks.
So this is about the layers in the neural network. So as we are going to build today on MNIST data set, multi-class classification, we are going to see how to add this hidden layers in between and finally get the output for a multi-class classification problem. So just a heads up, for a multi-class classification, we can be having more number of output units here as well. So instead of just one output one node in the output layer, we can have more number of nodes as well. So as we look forward, we'll understand. So now we just got a basic understanding of what a neural network is and what is the motivation of building up a neural network and how we can build complex networks by stacking up the layers. Let us look at the prime important part which we have been looking. This is the activation function part. So let's look at it. So activation function, as you once again, let's get back here. Till now, till this part, we are doing is just once let us look at this again. What we are doing is just adding the corresponding weights, and it is going to form a linear equation. This, but if x1 and x2, all these values are linear, if they are not of any other function values, this is going to be a linear function. So that means something like a straight line y is equal to mx plus c. So but that kind of y is equal to mx plus c might not work very well in terms of real world data. So real world data, let's take a simple example of heights of a students in a particular classroom. That small thing itself follows a normal distribution or a bell curve. That shows that the real world data is not linear. Like you cannot keep a real world data in the form of y is equal to mx plus c. It needs furthermore functions like either tan h or tan h or polynomial functions. Those are needed. So those are nothing but the non-linearities, right? A polynomial function is not a straight line, but it is a curvature. So non-linear functions usually have degree more, and they can easily represent a bell curve or normal distribution. So that's why we want to introduce this non-linearity into an activation function. uh, this is essential. So why are we applying this for neural networks is that neural networks are called as universal function approximators. What does that mean so with neural networks, the prime objective um, is to enable the network to learn anything. Like you want to create a relationship between any input value and any output value. Neural network, the neural network which you want to build should be able to do that. That is the objective. So that's why, since we want to replicate the real world data using a, like, make a machine understand real world, any real world situation with the help of neural networks, that is the objective. That's why we want to have non-linearities in the neural network. Okay, so that's why we consider taking up non-linearity in activation functions. So here an example of it. So this is a classification problem. So when we try to use just a straight line, this is, let's call it as y is equal to m1x plus c1. This is m2x plus c2. So these two lines, they are not able to classify the real world data. We want to classify it this way. So these two functions are not able to do that, whereas this curved function is able to do it. So that is the prime advantage which non-linearity and the activation functions provide us. Non-linearity in the activation functions provide us. Okay, so let's see further what is the activation function. If we do not apply an activation function, then the output signal would be a simple linear equation. We saw, right? It was just w naught plus w1 x1 plus w2 x2. It was just a summation of linear functions. So it can even become only a 1-degree polynomial equation. But because we want to use neural network for real world situations, which has like lot of curvature, we want to use this activation. If not, it just becomes a simple linear regression model. Okay, so only when we add this activation functions, the neural network will be able to read and understand complex kind of data like images, videos, audio, speech. All these it can learn only if we have this activation functions. So we need two important properties for activation functions. So those are, first thing, we want the activation function to be differentiable and add non-linearity. So we have already seen what is adding non-linearity to the model. So now let us see what is differentiability. So at this point of a very simple mathematical way to understand this, just draw a curve here. So a function is said to be differentiable if at a point you can draw only one tangent. So tangent is, so tangent, let's suppose we have a circle At a given point, we can at so we want, let's suppose there is a curve. At a given point, we can only be taking like drawing one tangent. But if you look at this function, and at this point we can draw multiple tangents, right? We can draw a lot of lines here at this point. So this function is not differentiable at 0. So two important properties which we look at activation functions are these two. First of all, it should be differentiable and it should be able to add the non-linearity. So today we'll be discussing mainly about these three. These three are the different activation functions which are normally used. So sigmoid, we have been knowing this. This is nothing but the logistic regression also uses the sigmoid activation. So this sigmoid activation, the in terms of it, the value it lies between is 0 to 1, and it adds the essential non-linearity. It is differentiable as well all over. Now let us take another activation function which we have is tan h. It lies between -1 and 1. Then comes ReLU, for which the value of ReLU is if it is lesser than 0. Like if the value of x is lesser than 0, it just takes that value as 0. And if the value is greater than 0, whatever is the value of x, that is what it is going to be. So it is nothing but y is equal to mx line, y is equal to x line. So whatever is the value of x, that's what you will be getting as y. So these are the three functions. Let us learn a little more about them in the next slides. So sigmoid function, as we have seen, it lies between 0 and 1. And I think we covered all of the problems. Sigmoids have, just remember this point, the convergence or rate of sigmoid activations is slower. This we will be using I'll more when we are going through the hands-on building of the model, then we will understand a little bit more about this. What is the slow convergence, faster convergence? Then we have tan h. So the main reason why we have come to this tan h is to avoid something called as vanishing gradient problem. This also I think will be covered in the future sessions, these two problems like vanishing and exploding. So let's get further. At that point you will be able to better understand the advantage which this tan h or the hyperbolic tangent function is providing. The next thing is ReLU. That is what mostly is being used for um, the nodes which are the nodes in the hidden layers. Okay, I'll tell you more when we build the model. So we understood the problem of we understood how it looks like. So for anything, for any x which is greater than 0, ReLU is nothing but the x itself. So a lot of times machine learning and computer science, we notice that most simple and consistent techniques are used and that are preferred. So it also avoids this vanishing gradient problem. Okay, then let's get further a little more. Just to give a little more idea. So as we have, for anything which is, for any x which is lesser than 0, it is all equal to 0 in ReLU. But there is a other variation called leaky ReLU, where instead of just making it totally 0, we are multiplying with some constant, so that it is not totally 0. Usually it is like 0.01, like very smaller values, so that it is not completely 0. We are even considering the negative values. And further version of this is nothing but the randomized leaky ReLU, where even these values are changing. It could have a range of values. So the main reason why we are doing this is that because for all the values which are lesser than for all the values of x which are lesser than 0, we are making y is equal to 0. That means we are actually killing that particular activation itself. It is equal to 0. So just to avoid that killing of neurons, in some cases we start using this leaky ReLU. So now let us look at the optimization functions.
Gayatri, I'm sorry to interrupt. So before we jump into the next session, there is one common question on live chat: why the activation function should be differentiable? This is a question. Yeah.
Activation function to be differentiable. Okay.
So I think we have mentioned that that is one of the
Property which is
advantages. Yeah,
needed.
yeah,
Yeah.
properties. Yeah.
I'm looking at the uh, mathematical perspective and I'm trying to come up with an answer to this. Okay, so this non-differentiability, what it does is that it totally makes the values, again for activation itself, it totally makes the values as zero. So particularly like if we are when we are building this neural network, this activation is primarily very important in the feed forward, like while we are feeding the network, and like we are forward propagation, right? So when we have something like which is non-differentiable activation, there is a possibility of killing of that neurons itself. So that is the reason uh, we we use this differentiability.
Okay. Okay. And okay, I think this part again, like, probably a few more questions we are getting. Why is the need for these activation functions? I think you have spent some time. Probably you can briefly explain again why is the need for these activation
Okay.
functions. Yeah.
Yeah,
And how
I'll
to
take you to that slide.
yeah,
Yeah,
and
one
also
second.
people were asking about how to choose the best activation functions, I think, which we will cover in later stages, or probably sometime in the middle of the session, or maybe at the end
Uh,
of the session. Yeah.
so why activation function? As I already told, these activation functions primarily they add this non-linearity. So if we don't have an activation function, there could be a possibility that we are not building a neural network but a linear regression model itself, which is just like y is equal to m1 x1 plus m2 x2 and so on. So but in a real world scenario, lot of the data is not in a straight line format as we have seen in this image. For this class, give me 1 minute, I'll try to open that image. Yeah, for this is just a simple classification problem, right? We are trying to classify. A straight line could not solve that classification properly, but a curvature could. So in order to create these curvature kind of functions, we need activation function. And how do we choose the best activation? So that's why I told you to remember that sigmoid results in slow convergence. relu uh, so relu helps us in eliminating some of the neurons, like creating some relu creates some of the dead neurons, like it doesn't take into consideration of the values which are lesser than that of zero. So depending upon the data set and the kind of problem which we are trying to solve, we have to best choose the sigmoid, and like we have to choose the activation functions. Usually for simple neural networks, what I have been seeing is that it is good to add relu for in hidden layers and sigmoid for the outermost um, output layer. So why relu? Because as I told, which you will be covering in the future sessions, the vanishing and exploding gradient problems, these are the two problems which we encounter in a neural network. So I'll just tell you what is vanishing very briefly and exploding gradient. In vanishing gradient, what happens is the total gradient becomes zero, like the values, the error, like when we are back propagating, the values become zero. Vanishing is zero. Exploding gradient, what happens is the gradient values will become huge. So these two are the two problems which we usually face because of the activations that we are using. So that's why depending upon the situation, we have to choose the best activation. So that's why usually why people use relu for hidden layers is that it solves these problems of vanishing gradient. Hope I made some kind of an intuition into this.
Yeah.
Okay.
Yeah. Thanks.
Yeah.
Yeah, I think it helps.
Yeah. So now let us look at, so till now activations, I feel, if you just recollect how a neural network works, for feed forward, activation is the main non-linearity which is adding. But these optimization functions help us in back propagation, like reducing the error across each neuron. For that, we use this optimization functions. So optimization functions are used to minimize or maximize the error function. So before even I use this word called optimization functions, let's be very clear. We all know about gradient descent, right? that is nothing but an optimization function. In a linear regression using gradient descent, we want to minimize the loss function, which is a mean squared error loss function, which we want to reduce, right? So optimization functions are nothing but the functions which we want to use to minimize or maximize error functions. Okay, for maximize, we in all the problems which we are trying to solve, we aim at minimizing the error functions only. So there are two types of optimization functions. There are first order, second order. This depends upon the differentiability that we are using. Okay. Yeah. Mm. So different types of activation functions which we have are gradient descent, stochastic, mini batch, adagrad, ada delta, adam, and we have even nested of other optimization functions. Each of them have been built so that they solve certain problems. So we will briefly cover what they do and what is the most commonly used optimization function as we go forward. So one more important thing, now I can either for the same question which has been asked before, why do we need differentiability, is even in the gradient descent, we are trying to differentiate the function and we are trying to remove the error, right? So if it is a non-differentiable function, which like either equals, if it is a non-differentiable function, we will not be able to compute this particular value. So it is for the optimization also that we need the functions, activation functions, to be differentiable. Okay. So here is a GIF which could help us understand. So this is a polynomial function. So for which is nothing but a cost and mean squared error. This is, so we are trying to come down, like we are calculating the through gradient descent. By applying gradient descent, we are trying to find an optimal point where the cost is totally zero. So this is where there is a minima of this loss function. So that's how, like, by traveling from here to here, we are trying to reduce the loss function using this gradient descent. So while we know about this gradient descent, an important thing which I want to recollect is, in a gradient descent, for every epoch, when I mean epoch, it is nothing but the one forward propagation plus one backward propagation is an epoch, right? So in a given epoch, let's suppose if we have like 1,000 data points in our data set, in a batch gradient descent, we will give all the 1,000 data points at a time. Just remember this point. This would help us further in understanding uh, the updated or like the variations of this gradient descent. So in a gradient descent or a batch gradient descent, total batch of the data, like if we have 1,000 data points, all of them at a time will be updated. All the weights corresponding to those input values will be updated at a time in a gradient descent, batch gradient descent. But when it comes to, so a little bit more intuition, we are trying to find out from the uh, our main goal is to find out the minima. And there is I will come back to this. I'll explain what there are the problems also after we discuss stochastic gradient descent. So as I told, in in a batch gradient descent, all the data points, like 1,000 data points, let's suppose the data set has 1,000 data points, all are being given at once. In stochastic gradient descent, what happens is, in a given epoch, we will give all the data points, but one by one. Like, the model will learn from each and every example in a stepwise manner. Even in the previous version also, the model will learn from all the examples, but because it is all at once, the impact is lesser. Like, the impact on the function is lesser in batch gradient descent compared to that of stochastic. I'll show you the pictorial representation, then you would understand. So see this in a, okay, this is forget about this mini batch gradient descent. We'll talk about it better. So let's suppose if it is a batch gradient descent, the optimization would be just could be a straight line. 1 minute, I'll try to use this. So this could be a stochastic grade. This could be a normal gradient descent. But if we forget about mini batch, I'm talking about gradient descent. But if we take up stochastic gradient descent, what happens is, because we are considering all the data points, it is going to have lot of spikes, like in the loss function, which we have seen earlier. So here, this is a loss function, it was a straight line, right? But if we are using a stochastic gradient descent, this could be like this. The line could be like this. Could be like this, because every data point's value is being considered in a stochastic gradient descent, and that is impacting directly. So now we understood a stochastic gradient descent. So what happens, in a given epoch, there are 1,000 times of iterations in a stochastic gradient descent, because here we are using each and every example, so the range is 1,000 here. Now let us take a mini batch. What is mini batches? I told we have 1,000 data points, so we will divide it into 10 groups, each of 100. So how many iterations we will have in this particular loop? We will have about 10 iterations, and in every iteration, 100 data points are being considered. So that means, instead of the model being affected by each and every point, that impact, see, if there is a lot of spikes like this, and every data point is not disturbing, if every data point is making impact, the convergence becomes slower, like it cannot reach faster. But if it is, let's take only batch gradient descent, which is directly going, then there is a possibility that it is not giving importance to the intricate details of the data. So how about an intermediate one, like intermediate one between gradient descent and a stochastic gradient descent, which is nothing but the mini batch gradient descent, which is taking the good things from stochastic as well as gradient descent. From gradient descent, it is helping us to converge faster compared to that of stochastic gradient descent. From stochastic gradient descent properties, it is giving importance to even the little bit of intricate details of the data. Hope I made some sense while I'm drawing a comparison between these three.
Yeah.
So yeah, stochastic gradient descent, it considers every data point, like it considers every example. That's what I tried to explain. Now, due to frequent updates, parameter updates have high variance and cause the loss function to fluctuate at different intensities. So that's what I explained here. So there could be a lot of fluctuations in the way this is going down that could affect the model further.
Gayatri, one quick thing. I think people wanted this. Can you please explain the spikes in stochastic bit, and also can if you can repeat the stochastic gradient and normal gradient bit, I think that would be great. Yeah.
Yeah. Okay.
Yeah.
So please closely observe this particular graph itself. Okay, this is an example for gradient descent. The original green, okay, the red one was for stochastic. I'll change the color. So now let me take this green one, and I will. So if it was a normal gradient descent, the loss function would have gone down simply like this. Okay, but because we are using stochastic gradient descent, because it considers every data point, there could be possibility of these spikes in here. So it could be like this, not just a straight line, it could be something like this. What I mean to tell is that each and every data point is directly impacting the cost function and the loss function, the way it is coming down. Now, obviously, because we are applying the gradient descent, the loss function is just going to go down. That is going to happen, but with lots of fluctuations compared to that of gradient descent. So what happens because of fluctuations? It takes much more time, right? If it was just like this, a smooth curve, it takes lesser time to converge. But if it is having like lot of spikes, the convergence rate becomes lower, and it converges slowly compared to that of batch gradient descent. Did I make some sense now?
Yes, I think it's clear now. So basically, like it attacks each and every point,
Yes.
whereas in the case of batch gradient descent, you take all the data points and do it in
Yes.
one shot, right? So yeah, yeah,
Yes.
it's clear. Yeah.
So the mini batch is nothing but an intermediate one of these two.
Yes, yeah, which is a combination of both, which takes the
Yeah.
properties of stochastic as well as the properties of batch and yeah. Yeah, I
Yeah.
think
This diagram should be able to like give an clear understanding. So if it has been a gradient descent, it would have been like this, not so straight line like this, just a representation. If it is a stochastic gradient descent, you can see it's like a lot of spikes. If it is a mini batch, lesser spikes and little bit faster convergence as well. Okay, so this is important. I mean, considering each and every data point is important, because we could have very intricate details. We'll discuss about it also in the disadvantages of this models. Okay, so as you can see, this is a live like a graph from stochastic gradient descent loss function. There are lots and lots of spikes. As you see, it is coming down, the loss is coming down, that's for sure, but it has like lots of spikes. So mini batch, as I told, like it is like an intermediate thing between stochastic and batch gradient descent. Commonly, now this is what is being in the neural networks. This is what we mostly use. Common mini batch sizes range from 50 to 256, but vary depending upon the application. Okay, so the size of this batch is also an hyperparameter which you can tune in. Okay. So if it was a batch gradient descent, it was a straight line. Mini batch, a little bit of curvature. If it was a stochastic, it would have got more number of curves like this, very more number of curves. Could be like this. If it was a stochastic, I'm referring to stochastic. Okay. So what are the challenges which we face with gradient descent? The first important thing is proper learning rate, right? So because we want to learning rate is the most important hyperparameter, which by tuning of which we will have we can create like that beautiful spot where that model is not overfitted or underfitted. That means the perfect model for the data. So this becomes little difficult. Also, we will apply the same learning rate across, like, so right, once you choose an alpha is what I think I represent as learning rate in a gradient descent. So once you choose alpha, you keep it the same, right, throughout, like in the equation here. Let me take you to the equation. So in this equation, eta is the learning rate. This is constant. We are not changing eta at all. So learning rate once taken is constant when it comes to this batch gradient descent. But that might not, I mean, the gradient descent or the variance of it, but that might not work as well. We might want to change this alpha to alpha 1, alpha 2. Usually we reduce the learning rates in practice. So we might want to change the alpha as well. For this, gradient descent does not inherently provide us that opportunity. We might have to add some extra code and do that. Another key challenge is minimizing highly non-convex error. Okay, so what happens? There is a possibility of getting stuck up with the local minima. So that's what this diagram shows. This GIF shows. Give me 1 minute. So here, this particular function is stuck up in this local minima, but we know that the global minima is this. So this is also an important problem which we usually end up with. We don't want it to stop it here. We want it to be actually come to this global minima. So that is also a problem with gradient descent. So AdaGrad, I'll explain very briefly about the three coming optimization functions. So because we are not changing eta, this is what the presentation is showing. Eta, which is nothing but alpha or the learning rate, different representation. Eta or this learning rate is constant in gradient descent unless we are adding some code. But what this AdaGrad does is we can change this. AdaGrad modifies the general learning rate eta at each time step. So AdaGrad automatically changes uh, the learning rate. So depending upon the situation, it changes the learning rate. So usually, let's take an example. When we are at the highest point of optimization, we might want to come down a little bit faster. Like we might want to use a bigger alpha. But when we are here, when we are reaching to the minimum point, we might want alpha to be very small. So that means depending upon where we are, like at which epoch we are, we might want to change alpha. So this thing directly is taken care by AdaGrad. So main benefit of AdaGrad is that we don't need to manually tune in the learning rate. Most implementation use a default value of 0.01 and just leave it. Depending upon like the epochs and depending upon the loss function, it adjusts itself. So then we are talking about Adam. So that's what we are using in our today's multi-class classification also. So Adam is what is like works well in practice, compares favorably to other adaptive learning based algorithms. This AdaGrad is also called as adaptive gradient descent. So adaptive because it is able to adapt, right? It is depending upon situation, it is able to change its learning rate. That is, it is adaptive. So of the same class of algorithms, adaptive learning based algorithms, Adam is also one, as it helps in convergence. Like we want fast, again, let me take the example. At this point of time, we want a very fast convergence. At this point of time, we want to slow a little bit because we don't want to jump in there. So it has a good convergence, it has a good learning speed, and it even solves the problems of this vanishing learning rate. So what is this vanishing learning rate? Is like learning rate becoming completely zero. So these kind of techniques also can be solved. And it it even does not like it doesn't have problem like very slow convergence or very fast convergence. So all the problems which we usually get with respect to learning rate and convergence with respect to the cost loss function to the minimum most value are solved by Adam. So that's why it is mostly used. So I think that should be it about optimization functions. So here, just take a look at it. If you want me to zoom in, I can do that. So this part, if you want me to zoom in, so see this. So we have used different types of, we only discussed AdaGrad and Adam, right? So there are others also like RMS prop, SGD nested. SGD nested is nothing but an extension of stochastic gradient descent and adding a momentum to it. These are a little bit of higher um, mathematical value. So AdaGrad, Adam. So if we look at the way these optimizations are like reducing the loss function, we see that Adam is able to do it much faster, right? This is Adam. This is AdaGrad, the first one which we the prior to Adam we discussed about AdaGrad. So this is how it was converging, and Adam was converging like this. So this could help us understand a little bit of how this works. Oh, I need to come up with this.
Maybe click
Yeah,
on escape if that
okay,
helps.
yeah. So now we understood about optimizations. Any questions to be discussed till now?
Yeah, I think we have few questions. Maybe I think those can be picked during the hands-on while we are doing the while we are at the optimization bit, or do you want to pick it now?
Yeah, I think you can put it forward. I'll, if we are going to discuss it later on, I'll address it at that point.
Okay, so one thing is how to decide which optimization function to use. That is one
Okay.
thing.
Okay.
And is there any advantage of using stochastic over batch?
Yeah. Okay. Um, the stochastic part, as I explained, uh, it was considering every data point. So that's the advantage. But that becomes a disadvantage as well because every data point is being considered and like every small fluctuation is being considered. So usually we do not use either like unless a problem statement specifically requires us to use, we will not use either the only gradient descent or only stochastic, but an intermediate one, which is mini batch. So the other question will be addressed as we are going forward.
Yeah.
So now let us look at this multi-class classification using artificial neural networks. So a simple representation to help us understand. So it's just classifying the things or predicting different classes. So instead of just predicting yes or no or 0 or 1, we might need to predict 0, 1, 2, 3, 4 different classes. So here we have 4 different classes. This is as simple as that. We are just trying to group things into different classes. So how we are going to achieve that with the help of neural network is what we are going to see further. So for that we are using MNIST dataset. So this is an image dataset consisting of handwritten digits. So different people will be writing this handwritten digits in different ways, right? So this particular dataset has about 60,000 training images and 10,000 test images, each of 28 by 28 size. Excuse me. So these images are available. What we are trying to how we are trying to solve this multi-class classification is that when we are given a set of images of 4, set of images of 5, we want our model to predict that this is 5, this is 3. uh, our model to understand, because this 3 is different from this 3. So but even then our model should be able to tell that this is 3. So that's what we are trying to predict using this MNIST dataset. Okay, so let's get into the Jupyter notebook and understand how to build the model and how to play around with it. Uh, so, with respect to this particular notebook, the agenda is to go understand what is the data, and we will look into how to load the different libraries which we need, and then loading data and pre-processing, and then building the model. So, while because the main focus is how to build the model, we will see how to play around with different values and like play around with how like even see how to tune certain parameters as well. So as I already told, MNIST is a dataset consisting of 70,000 handwritten digits. So 60,000 come for training and 10,000 for testing. So let's see how to build. So the first step which we are trying to do here is load the essential libraries, TensorFlow, NumPy, and Matplotlib. Okay. So for loading the data set, it is simple because MNIST is such a popular data set. So there are versions of it like fashion MNIST data set also. So because it is so popular for among the beginners of deep learning, and like anyone who wants to start learning about this deep learning, this is something which we try to learn upon. So that's why this is very popular, and that's why it is directly available with TensorFlow or Keras. So the frameworks themselves have these data sets. So all that you need to do is just use this line from tensorflow.keras.datasets.mnist import load data. That just imports the data for us. Then let us see. I because we have seen about it. I told you that it has like 60,000 in training and 10,000 in test. So let's see it with the code. So and also each image. So each image, as we have seen earlier here, it is of each of size 28 by 28, as I already told you. So that's what we are trying to get the shape. So that 28 by 28 is in mathematically, it's looking like this. See the different values. So this is where we have actually have the number. All these zeros correspond to that black part, or I think the white part, or yeah, all the zeros correspond to that black part, and the rest where we have all these numbers is the different pixel distributions of this particular strikes or strokes of this particular number. So this will give you a lot more understanding. So nothing but I have 1 minute. I have actually collected an image as well. Uh, so this particular image helps us understand that. 1 minute, I'll try to open the image. Which, that gives a little more understanding of
Yeah, I think MNIST data image or maybe, and also
So I think all that I want to make you understand is that these values correspond to the pixel distribution at that particular stroke, and these zeros correspond to the place where nothing is there. That's because we are able to understand even the pixel values. This MNIST forms as a very good beginner data set, so that we understand how an image pixel distribution across an image looks like also. Towards the end of the session, I'll search and I'll show you that image, which gives you a little more understanding. So the same image, okay, the same image as we have seen before, it was all numbers. That same thing with different pixel distribution is spread across like this. So let's try to see it as an image itself now. Now we can, what is this image? This is nothing but 5. So let's cross check and see what that our labels have. And that is also 5. So this part of the code I just added so that we can see the different numbers, 5, 0, 4, 1. Then, so this is how the images are right now. So, and we know that if you see the numbers here, they are of different range, right? From what is, if you anyone has observed, the range is usually something lesser than that of 255, right? So the range of these numbers is 0 to 255. So that means the range of the values could be, if everything is black, it was 0, and everything is of different colors, it is of some values, and finally, if it is totally white, it is like 255. So that's what we have observed. So that range 0 to 255 is like huge range. We want to get everything into a range of 0 to 1, and that's why we are applying normalization. So how do we apply? So the normalization is, what is the motivation for normalization is to achieve consistency in the dynamic range of set of data, signals, images, to avoid distraction and reduce data redundancy. So as I told, because this data is like 0 to 255 range, like different values, by normalizing and bringing it into 0 to 1, we are actually trying to build something closer to that of a normal distribution. We are trying to build something like that so that we can directly apply our model later on. So for normalization, because the range is from 0 to 255, we're just dividing the training data set and the test data set by 255.
Yeah.
Okay.
Gayatri, I think people people wanted some clarity about that 255 thing. It's the range of the pixel, right? Or
Yes, yes.
yeah, it's okay, great.
Yeah,
Yeah,
it's the
thanks.
range of pixel values.
Yeah, great.
Uh, so now, earlier it had the values of this range, like it was something like 186, 253, like that. So now these values, uh, now these same values after being normalized are looking something, they're lying between 0 to 1. This is 0.99. So should be the brightest point. 0.15 should be a little bit lighter point. So if you see the image here earlier, we could see that over the strokes, certain lines were very certain. This point is little bit lesser bright compared to that. This is the brightest point. So these different points have different values, and that all we normalized to lie between 0 and 1, as we can see. Okay. Uh, so after this, if we look at this particular image, so if you if we look at this images, they are in 2 dimensions, right? So this is a 2-dimensional image. This is a 2-dimensional image. This is a 2-dimensional image. Now, but we want to convert them into a single dimensional. So since this image is 2-dimensional, the total we got a matrix here. If you see, this is a numpy array with two. It is of dimensions of 2. So that's why, so since it is a 2-dimensional array, we want to convert it into a single dimensional array. So why do we want to do that? I'll tell you as we build the model, okay? So just remember, now we are trying to flatten, instead of having this 28 by 28 2-dimensional matrix, we want to have something like a single dimensional uh, 784, yeah, 784 valued vector. That's what we want. So instead of having this 2D array here, for each for each image, we want to have a 1D array. I think I'm making some sense. So let's see more about it.
Gayatri, one quick thing. Why are we standardizing? That is one question that people are asking.
Standardizing in the sense?
We are standardizing.
Normalizing?
Yeah, we are normalizing, right, by dividing it by 255.
Yeah.
Yeah,
Yeah, that's what we have addressed here, right? 1 minute.
yeah.
So for the different range, because if we have this dynamic range from like 0 to 255, which is a huge range. So for different types of data sets, like signals or images, it could be like it could create data redundancy, and some kind of it can be adding some noise to the data set. So we want it to be in a range, and we want to like bring it closer to that of a normal distribution, so that we can apply the model much better. So
Yeah,
what is what
yeah.
what what I meant when like bringing to normal distribution is, uh, so because as I told, this is a real world data, and most of it like is like a bell curve. So our objective would be something getting closer to that of bell curve, so that we can apply any model more clearly. Because as we know that neural networks also are built think like are built so that we can create something, we can apply them and make them understand how a real world data set looks like, something closer to normal distribution. That's why we want to apply this normalization. Just to keep it very clear, if it has this lot of dynamic range, there could be a lot of noise in the data. We don't want that. That's simple, as simple as that. So we have then we can see it is a there are about 60,000 images, each of size 28 by 28. So this is a uh, three-dimensional array that we have. So that thing we want to convert it into a 2D array representation. So that would be all the data, all the images, which are like 60,000 images, which we have, are before like this as a matrix. Now that we are trying to convert them into a single dimensional vectors. So let me show you, here we have the representation. So this is the image. And when we have the values, like in the thick, brightest spots, there are some values like 87, 240, 210, 24, and all the darkest spots are all zeros, right? And this is a matrix. Now this is just one of the 60,000 images we have. So like this we have 60,000 other images as well. We just took one of those. We have seen it mathematically in a 28 by 28 grid. This one, we don't want it in 28 by 28 grid. We want it to have a straight line. So how we are doing it? We are trying to flatten and convert it into a 784. Like there are 28 by 28 is equal to 784, right? So those many number of values are being stored in a single straight line. So how are we flattening it? Just simple. Just we are trying to place these 28 by 28 values, and then the next 28 in a straight line. We are just stacking it up column wise. We can think like that. So once we are done with that, we can now like this. So this is just one image, that is one vector. So how many images we have? 60,000. That means how many vectors do we get? 60,000 vectors, right? Okay. So while we are building the model, we'll understand further more about it. Okay. So the idea is the 60,000 images, which are like matrices, or which are like image format. We want to convert those 60,000 things into vectors. So that is constructed, and then 784 neurons have been taken up in the input layer to take up all these 784 corresponding values. Those, because in the first model, like we want to use only a single layered neural network, which is just when I mean single layered, I mean it has one input. Never consider input as one of the layers. Input is independent. When I mean a single layer, it is just a single output layer. When I mean two layers, there is an output layer, there is an input hidden layer. So when I mean three layers, there is one output layer and two more hidden layers. Okay. So in this single neural network that we want to build up, so first we have taken up the number of neurons in input layer, which is equal to that of the corresponding length of each vector. And then we have applied the activation, which we saw in the earlier representation. So in the earlier, okay, let me just take there very fastly. So in the same thing here, first, these inputs have been taken, and this is nothing but the activation, which I'm trying to refer to here also. So first we tried to do the summation, then applied activation. That's what we did here, right? First we did the summation, and then we applied the activation. Simple. And then, because now what we are trying to do is, there are about different images of different handwritten digits. So there could be, like, these images are 60,000 each. So what is the total number of classes that we can have? 0 to 9, which is nothing but 10 classes. So any image here can either be 0 or 4 or 1 or 2, but it cannot be anything else. So then how many number of classes we can categorize this particular data set into? Is 10 classes, right? So that's why, because we want only 10 outputs, we will take 10 outputs, 10 neurons in the output layer. So this corresponds to 0, 1, 2, 3, like that till 9. So each neuron corresponds to one output value that we want to obtain. So that's why this output layer has got 10 neurons. And why does this have 784 input neurons? Corresponding to each value in the vector, we have 784 inputs. Hope I'm clear with why we are taking the number of neurons in each layer. So that's what earlier in the first neural network that I showed you here, this one, it was just having one output value, because it was just trying to classify two things, or it was just trying to predict any of two classes. It can only do classify into two classes, which is like binary classification. But here we want to predict any of the 10 values. We are taking 10 different neurons. Let's go a little further. So that's why now we understood it has. So let me just tell you again. So our neural network, the simple neural network with single layer, has got 10 nodes in the output layer and 784 nodes in the input layer. So now that's why I have given, this is Keras sequential model, a sequential framework that we are using. It has two different models, sequential and functional. So we are using sequential here. In this dense corresponds to the layer. So here dense is nothing but the layer that we are formulating. So how many layers do we have in this particular model? Only one, because I told we shouldn't consider the input layer as a layer. It is the input which is being given. So these in the output layers that we are having single layer, which has 10 units, because we want to classify into 10 different classes. And we have an input shape of 784 by 1, right? Because 784 neurons. And what is the activation that is being used? Sigmoid. So why are we using sigmoid here? Let's see. Sigmoid, when it comes to, like, it has slower convergence rate, but when it comes to classifying things, and like, it can bring about the values. So if you see the sigmoid itself, it lies between 0 and 1, right? So bringing the values to 0 or 1, or classifying part, can be done very nicely by sigmoid. So that's why usually the output layer consists of sigmoid activation. So let's run this. So here, by using this particular statement, we are able to define the model. So we have defined the model. So let's look at it. So once we define the model, this is a simple model, we know it. But like, when we are having multiple layers, when we start adding multiple layers, we might want to know what is the total number of parameters, what is the total number of neurons. So for that, use this model.summary. That will help you understand what is the number of layers, what is the shape for each layer. So whenever you keep adding a input shape, whenever you keep adding a layer here, we will do it further. This is a simple layer. So when we keep adding layers, the corresponding layer values and the corresponding output shapes will be given. So that, because we are actually doing dot product, right? Anywhere here, what we are trying to do is, we are trying to multiply the corresponding weights to the input layers and apply activation. That's what we are doing. So if we don't understand these sizes very clearly, like if we don't understand the shapes clearly, we will start getting a lot of errors. mainly this dot product related errors, we keep getting key errors and all that. That's why it's good to look at the model once you have stacked up the layers and defined the model. Just have a look at it and understand if the shapes are compatible. Okay, so we have seen what our model is looking like, and we don't have any problem with those kind of matrix multiplication because it's a simple network. Now, um, so now we can compile the model. So here, when we are compiling, we are applying what is the optimization function? It is Adam. And we are using sparse categorical cross entropy. So for regression, is the loss function which we use is usually the mean squared error. So here we are using sparse categorical entropy. Why is it so? Is that because here we are independently trying to predict there are 10 different classes. 0 is one class, 1 is one class, 2 is one class. So when we have something like this independent classes which are like integers, we go for sparse categorical cross entropy. So in the notebook which will be shared with you also, there is this article which explains why we are using sparse categorical cross entropy. So simply it is because we are having different classes which are independent of each other. So 0 is not dependent on 1, right? An image which is showing 0 will never be like, which might not be very close to that of how a 1 looks like. So when we have independent classes like this, then we go for sparse categorical cross entropy, and the metrics which we're using is accuracy metric. Okay, so let me compile it. Now, after we have compiled, so there are 3 steps in model building. Keras really makes it very simple. First thing, you just need to define the model, and if you want to have a summary look at it, and then compile the model, define, compile, and fit the model. That's it. So what I mean by fitting is that this is the point where I am feeding in the input values. So all this transformation that I have done earlier here, all the flattening and all the pre-processing I have done to the input data set will be coming into the picture at this point. 1 minute. So at this point of time, I will I will feed in the input data and the input labels. So now the model will start learning. Okay. So let's see how it is learning. Here, what is epoch? One epoch is nothing but one forward propagation plus one backward propagation. So we are taking about 5 epochs. So after 5 epochs, let us see what is the loss and what is accuracy. So if you look at it, the accuracy is 92%, right? And the loss is 0.26. Okay, looks good. Now let us see further what we can do. Let us try to, if you increase the epochs here, also let's try to make it 10 and see just very fastly. Let's see, because also I have already trained the model, right? So that's why the loss has begun from 0.26. So it is not at the 10th epoch. It didn't start at 0th epoch. It started at 6th epoch, if you see. So for the already trained model of 5 epochs, I am again training. That's why the loss is further reducing. The loss is further reducing and the accuracy has increased. Earlier it was 92%, now it is 93%, right? So play around with this. You will see that the model is increasing in terms of accuracy and the loss is reducing. So after that, we want to evaluate the model because on the training data set, the model has learned. Now we want to test it on the test data set. So model.evaluate. So here we can see that the loss is 0.25. The accuracy is still 92%. That once we have trained the model, when we look at it, the test data set, we saw that it has got 92.97%. Okay. So because we have, it's not like 10 epochs, we have done actually for 15 epochs. That's why the accuracy is increased from 92.6%. For it was for 5 epochs, we were getting 92.6. So because it's for 15 epochs, because I increased the number of epochs, it has now become 92.9. So when you, yeah, any questions?
No, nothing. I think 15 epochs thing. Maybe if you can come again. So initially we have run 5 and then
Yeah.
we
So
again
what
changed
happened
it.
is because it's
Yeah.
the same model, right? I
Yeah.
didn't initialize the model again. So because it is already a learned model, again on top of it, I changed to 10. That's why it is learning on top of it. Okay, let me make it 0 and then show you again. So now it is 10 epochs. Let's have a look at it. See how where the loss function has started. It has started at 0.48. Earlier it started at 0.26. Okay, let me not confuse you. Just have a glance at it. So with 10 epochs, we got about 93.1% accuracy. So let me take 15 epochs once, and then we will go to the next section of the code. Just remember it was 93.1, right? So let's see what we will get now. Yeah. So it has already started to cross that 93.1 and it is now 93.2. So the accuracy has now become 93.3. So for 10 for 5 epochs it was 92. For 10 epochs it was like 93. Now it has further increased. So since epochs is a hyperparameter which you can tune around and play around and see how this accuracy is changing. Now let us see for the test data set. Test data set also there is a little improvement. It instead of like earlier it was I guess 92.7, it has become it's further increased a little. Okay, so now let us predict the values. So for that we use model.predict. Okay, so after this we will try to even look at it. So the value which we got is now the above numbers are the probabilities for different digits. So this is what we got as the probabilities across all these neurons. So the final 10 neurons have given us these values, range of values. In that, when we applied the argmax, like the maximum value out of all these, when we applied it, we got it to be 7. So our predicted value is 7. And our actual, let's see the actual data set also and see what it is. It is 7. So our model is able to predict correctly that this image which it has seen is 7. Now till now we have understood that it was only a single layer neural network, right? Only a single layer. Now let's try to add one more layer to it. So this was the first okay, give me 1 minute. So this was the initial input layer. Okay, this was the first hidden layer, and this is the final output layer. So what I'm trying to do is, okay, for this output layer which we have here, give me 1 minute. This could be better in understanding. Okay. Yeah. So what I'm trying to do is, till now we have been dealing with the only output layer. Now I'm adding this first hidden layer. So forget about this. This is not there. This hidden layer is not there. There is only one hidden layer, one output layer. But in our case, the output layer has 10 nodes. Here it's showing only one node. So we are adding this layer now. So let's add it. So for that, in the first hidden layer, we are adding about 100 neurons, and the input shape is 784 because that is the number of input nodes that we have in the input layer, and the activation which we're using is ReLU. As I told, because this ReLU solves the problem of vanishing gradient and particularly vanishing gradient, for hidden layers, we usually use ReLU. So that's why we use this activation as ReLU. And this final, the next layer is nothing but the output layer. Only one layer, one hidden layer has been added. So as I told, for the output layer, usually we use sigmoid, and we have used the sigmoid itself here. So hope I made some sense. So this particular neural network has about one hidden layer here and one output layer. And then for the same thing, I'm applying model.summary. So here, if you see, this is the layer which is being shown, and it has 785,000 parameters because of 100 neurons that we have added. And this is the final output layer, and this is the first hidden layer. So the model also shows the same thing. Good, looks good. So let's get forward. So again, now I'm compiling the model, same Adam and same Sparse categorical loss function and metrics we are using are accuracy. So no change in this. We have compiled the model and we have applied, we have even applied, like we have even fed the model with the data. So here, earlier we didn't have any batch. Like in this fit part, which 1 minute. So here it was only input data and the output data and epochs. That's what I have given. But here I try to include the batch size also. So what I'm trying to do is the 60,000 data points we have, right? Each one of them, I'm trying to divide it into some set of batches. So each batch size is 128. So what does this mean? This means that earlier we were using something like batch at a time. It is not gradient descent. We are using Adam optimization, but something like a total 1 minute, something like total data set is being given as a single batch here. But now I thought I'll even, because we discussed about mini batch, let's try to look at it. So what we are trying to do is, instead of just giving total 60,000 data points at a time, we are giving it in the form of small batches, each of size 128. And the epoch size, I have put it at 5. Let's play around and see. Okay. So what are the two changes we have done to the previous model? We have added a layer and we are just giving it in the form of batch, small batches. Okay. And let's see. So we can see that right now the accuracy is 97.3. So now let me change it to some 20 epochs and let's see what happens. Okay, sorry, didn't change it. Earlier, what was the accuracy we saw? It was around 97 point something. So now we can see that it is already coming closer to 99. So it is 99.66 on training data set. So now let us see on the test data set. Test data set, it looks like 97.8. Okay. For the further, earlier it was for 5 epochs and we saw some 97.5 and it is like 97.8. It's good, but further, like if we keep increasing epochs for a long time, like 100 200 something like that, at a point you will not see any change in the kind of accuracy. That is something which you should see, like play around and see that if you add like a lot of epochs, what happens to this data set. That will be a really good observation. So after we got how to train the model and test it, now let us see how to save the model. Okay. So I have created a directory called results, and my model name is kirazmnist.h5. The model is saved in the form of HDF5 file format. So after that, I just saved it at this particular location. So that's how we can save the model, and this same model can be reused again and again by Keras has this load model function. Just by using that, we can. So, what is this particular H5 store is that all the parameter values of each node and all those values will be stored in here in this H5 file, which can be used for further use of the model or for the deployment or even building on top of that particular model as well. So like for when you want, there is this thing called like transfer learning where one model which is already built will be used to build some other model. So for all those purposes, saving model will be really helpful. So it's good to save the model at a particular location. So so we have already come to this summary part. So today we have seen while we have seen about activation optimization, we have seen why do we need to normalize, flatten the data, and what happens like when we have 100 hidden neurons in a particular hidden layer. And okay, so then we can why we have flattened this particular data for this particular and for this particular neural network. Okay. Uh, yeah. So I'm. Any questions can be asked now.
Yeah, great, great. I think yeah, thanks. So I'll probably quickly go over questions, and then we can yeah, pick one by one. So one question is, why was sigmoid function used in the output layer? And I think it was in the first model that you have built, right, where we were only picking one layer.
Yeah. We have even in the second model also we use
Yeah,
sigmoid
we
for
use
the
sigmoid,
output.
and then in the hidden layer we have used ReLU. Yeah.
The primary advantage is because the way it is able to see, even for logistic regression also we use sigmoid, right? So the way it is able to classify things gives us that edge. So that's why we are using sigmoid.
Okay. And how to choose hyperparameters? How to choose the number of neurons in hidden layers?
Okay. So um, I for this I would say just go around, use how many number of neurons you want, just play around with it and see that at some points you will not see any change in accuracy. Like the accuracy, actually the test accuracy starts reducing. So that is called as the model is what happens is the model performs very well on the training data set and does not do very well on the test data set. But in real world we want it to perform on test data set. So this scenario is called overfitting. So when we see such kind of an overfitting or something, usually in neural networks, overfitting is the problem. Just read about it, you will understand more. So in order you avoid these kind of overfitting, like when you understand about this overfitting kind of problems, you would get to know that depending upon the data size, like what is the size of the data that you have, and what is the depending upon your data set and depending upon the complexity of your data set, choose to build a model. Like for a very small data set, like it has only like let's suppose it has just like 1,000 data points. For that, don't build a model which has like 100 thousands of neurons, or that would not be needed at all. So depending upon the complexity of your data set and the type of the problem statement, keep choosing the hyperparameters.
Yeah, and so hyperparameters need to be chosen manually, or are there any optimization techniques out there?
No, they have to be chosen. Hyperparameters have to be chosen manually. That's what usually comes in that validation part, like cross validation. So while we are doing validation, we usually tune these hyperparameters.
Okay.
Uh, but I mean, we can automate certain things related to hyperparameters. Like we instead of like manually uh, m- changing the hyperparameters and testing it repeatedly, we can automate that part, like using some Python code. But there is nothing like totally automation. That
Okay.
comes out of intuition of the practitioner.
Okay. And is flattening done in every use case, or?
Uh, so in every use case, we don't need to flatten. So if you are having layers like convolutional layers, okay, this is the new thing I'm introducing again. So if we are in this case, why we are like creating a vector is that in a neural networks case, it wants to be fed with the vector. So I think I can safely say that in case of neurons, you would need to flatten. But if you're adding some extra layers like convolutional and all that, you would see that you don't need to flatten initially.
Okay. And can you explain about validation data briefly?
Okay, so in this data set, we have 60,000 data points, right? Training, and 10,000 were test, which are like already allocated. So out of this 60,000 data sets, instead of just using all 60,000 data sets for training, what I would do is take some 40,000 for training and use those 20,000. So whenever, instead of, so what did we do here? So we have fitted and trained the model. After fitting using all the epochs, I finally tested on the test data set. So instead of doing that, it's just 15 epochs here, but usually like hundreds of epochs could be there. Then what I would do is, for every, let's suppose I have 100 epochs, for every 20 epochs or for every 30 epochs, I'll include a part of code which does validation then and there itself. So that would help me understand if my model is performing well. So that I might, so instead of just waiting till 100 epochs to finish, which takes a lot of time, I would see in between and see how the model is performing on the validation set, which is almost equal to that of test, because for validation, training data set, we would give input as well as output. But for validation, it is almost equal to that of test data set. I wouldn't give it a test data set. So that would help me validate that my model is going in right direction, so I can continue training
Okay, got it.
even prior to the final testing. Yeah.
Yeah, and also maybe if you can go through the and explain the flow of input into the model once again, I think that would throw some more light. I think this was something that is slightly, I mean, like there are a few questions on that.
Okay. So this image, it is one image, and we have seen how to feed one image into a neural network, right? Through this vector. So like this, we have 60,000 vectors, and all of them are being fed into this neural network. So what is happening is, it is a, it is 60,000 of these. So here we have one vector, like that we have 60,000 vectors here. Just I'm trying with my cursor, I'm trying to do straight line. So there are about 60,000 vectors, each of size 784, and that is being fed into the network. So
Okay.
I can safely say that the number of you will have as many vectors as the number of data points you have, training examples you have, and each vector corresponds to the features of it. And here the features are nothing but the pixel values represented in the form of a vector. So I can say that x1, x2, x3, and x8, 784 are nothing but the features of this data set.
Right. Yeah, got it. And yeah, how to choose how many hidden layers in a given data set? I mean, how do you choose
And
how
that is
many?
again a hyperparameter, just like how you would play around and decide the number of neurons in each hidden layer. You
Yeah,
would have to play around and see how many layers you would need.
right. And also for the hyperparameter tuning, right? Can we use, I mean, I think we can use techniques like grid search,
Yeah.
random search. Yeah.
Yes. Yes. Yes.
So, and how to reach global minima, that is avoiding local minima.
Uh, so in order we achieve that, only we are using different optimizations and different activations, right? So we saw that gradient descent. Let's talk only with respect to optimization now. We saw that the gradient descent was having those saddle points here. So when we took the example of gradient descent, yeah. So this had a problem of getting stuck with the local minima. So that's why we moved to, instead of using gradient descent, we started moving to ADA, grad, Adam. So these optimizations help us not get stuck with the local minima.
Okay. And also, Gayatri, if you can go over this again, why? So we have used sigmoid in the output layer, right? And also in the hidden layers, we have used ReLU. So can we use it interchangeably, or how do we go about
So what
picking those
happens
activation functions?
when, if we use sigmoid in the intermediate layers? I told sigmoid has a problem of slow convergence, and it has this problem of vanishing gradients. So what I told, vanishing gradient is the values becoming zeros. So if something like that happens, we will get, like, the model will stop learning. So that's why it is not good practice to use sigmoid in between layers. uh, ReLU is something which solves that, like, uh, as we discuss more about vanishing gradients, I think it would more make sense. Uh, okay, let me take it to the
Yeah,
slides again.
I think that covers to a lot of extent, like what
Yeah.
you said
So,
right now.
uh,
Yeah,
primarily to solve this problem of this vanishing gradients and uh,
yeah,
the values becoming totally zero, we
yeah,
want to use something like ReLU for intermediate layers.
yeah. To maintain that continuity in learning. Yeah, got
Yes.
it. And also, if you can briefly summarize, or what are the differences between grad and Adam?
Hello.
Yeah.
There was some disturbance and I couldn't hear you.
Yeah, I was asking, can you briefly explain about the differences between Adagrad and Adam?
Okay. So let me take you to the slide again. So EdaGrad, as I told, primarily what it helps us do is to um, change the learning rate adaptively depending upon the situation. But though it is able to do that, it is not able to solve certain problems. I think it is related to momentum and the way the learning rate is being changed. But like Adam tries to solve even those problems, like even the problems which are related to parameter updates. Um, Parameter update, I meant primarily for learning parameter update. Um, the way it is able to change the learning rate depending upon situation. Apart from that, it even solves the problems which are related to momentum. Momentum is like the speed at which we are able to converge.
Okay, got it. Yeah, yeah, and yeah, I think with that we are done with the questions. Thanks a lot, Gayatri. That was I think it was the session was very engaging, and we can see a lot of thanks pouring in on the live chat. Thanks a lot for such a wonderful session, and also thanks to all the audience uh, for being there all throughout, and for engaging questions and all. Also, Gayatri, any insights on what kind of um, so you have worked in the industry, right, and you have applied deep learning. So if you can throw some light on what kind of applications you have worked on, or what kind of transformations that you have brought in by using deep learning, that would be great, I guess. Yeah.
Okay. Uh, so primarily, the first in the first in the natural language processing, we were trying to, like, the problem statement which we were trying to do is get the semantics. I mean, make a machine understand natural language, which is nothing but English. For that, we were trying to use deep learning, like the NLP models which are built on deep learning. So that was one area which I worked. The next one was for this algorithmic trading, like when we want our bot to be able to tell when we can enter the market, when we can come out of the market, so that we can make good profits. So for that, we were using a combination of reinforcement learning from machine learning and deep learning. So it was deep reinforcement learning, where we were first building a reinforcement learning agent, and that was the knowledge of that was again being used to build this neural network. And finally, neural network was learning lot of, I mean, was learning from its prior agent, which is reinforcement learning, and it was giving the outputs.
Nice.
So it was like building up using two different types of learning agents,
Nice, nice.
of which this neural network was very important.
Right. Yeah, interesting. And also, I think the computational bit and also optimization plays a big role, if I'm not wrong.
Yes, yes.
So how do you handle it when it comes to putting them into production, or even before, while building the model? So
So, particularly while building the model, as I told, we would um, look at, so instead of, because it's a huge data that we have, which keeps pouring in, and also the huge number of epochs which we have to keep training. There were times like 8 to 9 hours of training. We cannot
Mhm.
wait till the end and like waste the productive hours. Like, so in between, we used to come up with strategies so that what could be the next hyperparameter set, or the grid search, like what could be the next grid that we will be using, so
Mhm.
that after this test we can start preparing for the next one. Like particularly for hyperparameter tuning, we used
Yeah.
to do this. And also, like using these interactive boards like tensor board and all that, that would make us understand like whether our model will be able to learn or not, or we need to go through other models. So while the model is being trained, we would spend certain amount of time on research papers as well to
Yeah.
see some what else can be added. Yeah.
Nice. Interesting. Yeah. And any tips or like, any suggestions, thoughts that you would want to share with the learners before we end the session?
So I would suggest like lot of the problems are being solved with this particularly neural networks and deep learning. Like techniques like so many are coming up like BERT in which we can use in NLP, and even models like recently what I worked on for image processing was with Detectron. So that was for object detection. So lot of problems are being solved by this deep learning. Like there are every industry has got some scope of this deep learning for sure, because it is trying to replicate the way humans can think. So that's why just after you finish the boot camp, just to select one area which you would find industry interesting. Like if you like something related to language, and go with like NLP, linguistics. And if you like something related to images, computer vision, go in that direction. So once you finish the boot camp, just select an area where you want to work on, and build profile, so that that talks much better than anything else.
Yeah, nice, nice. That's very insightful. Thanks a lot, Gayatri, for joining us, and also thanks a lot to all the audience. Thank you, Julian. Thank you, Gunika, and thank you, Raviraj, for being there and addressing all the questions on live chat. Thanks a ton, and stay tuned. I think the next session is on 29th, if I'm not wrong. That's on Saturday. And meanwhile, we have also I think we have put up two quizzes. Please do it on time, and we'll be coming up with more exciting stuff very soon. Thanks a ton. Take care. Bye. I think the next session is on